On August 27, 2016, a hush fell over a room at NASA's Jet Propulsion Laboratory. Scientists were listening intently for signals from a spacecraft that had been journeying through the void for 5 years. This craft had traveled more than 1.5 billion miles, alone and silent in the vastness of space, and finally, its data began to stream in. Scott Bolton, a seasoned scientist, stared at the readings on his screen, readings that defied everything textbooks had taught about Jupiter's core for decades. The solid, compact core that everyone expected simply wasn't there. Instead, what Juno found on that first flyby was something entirely unexpected. Bolton would later call it a surprise, a word heavy with meaning coming from a man who had spent his career preparing for this mission. Jupiter had been waiting all along, just waiting for someone to come along and ask the right questions. Juno's journey began on August 5, 2011, when it launched from Cape Canaveral, Florida. This 4-ton spacecraft didn't look like your typical Jupiter explorer. Its path wasn't a straight shot. It first crossed Mars' orbit, then swung back toward Earth to use our planet's gravity as a slingshot, a maneuver called a gravity assist. In October 2013, Juno returned close to Earth, not to land, but to steal some of its momentum. Earth boosted Juno's speed by more than 16,000 miles per hour, flinging it outward, away from the inner solar system for good. After the long cruise, Juno arrived at Jupiter on July 4, 2016. The approach was nerve-wracking. To slip into orbit, Juno had to ignite its main engine for exactly 35 minutes at precisely the right moment. Fire it too early, and the spacecraft would miss the planet. Too late, and it would fly right past, ending the mission before it started. Signals took almost 50 minutes just to travel between Juno and Earth, so the spacecraft had to execute the burn entirely on its own. It nailed the timing within 1 second. The team at JPL, monitoring streams of data rather than any live images, finally exhaled. Juno was in orbit around Jupiter. But then came the first twist. The original plan was for Juno to perform 2 long orbits each lasting 53 days, then fire its engine again to tighten those orbits to about 2 weeks for the remainder of the mission. Shorter orbits meant more passes, more data. However, when engineers checked the engine, some valves weren't working as expected. A failed burn could be disastrous. After weighing the risks, the team decided to keep Juno in the longer orbits indefinitely. This meant that each flyby would still offer a 2-hour window to collect data, but those windows would come every 7 weeks instead of every 2. The mission would stretch out longer than planned, but it would yield discoveries no one anticipated. From that very first data return in late August 2016, Jupiter began to reveal itself as far more complex than anyone had imagined. Starting with the clouds visible even from Earth, these aren't just pretty stripes. They're the surface of a violent, restless atmosphere. Juno's instruments showed that the colorful bands circling the planet, the dark orange belts alternating with lighter zones, are actually enormous rivers of wind, racing east and west in opposite directions. These jet streams collide and interact with immense energy. One question had long puzzled scientists: how deep do these winds go? The answer, unveiled by Juno's precise measurements of Jupiter's gravity field, was astounding. These jet streams plunge nearly 1,900 miles beneath the cloud tops, far deeper than anyone expected. That's nearly 2,000 miles of turbulent atmosphere, extending down to where Jupiter's inner layers begin to shift. Up near the cold upper atmosphere, water, ice, and ammonia mingle in curious ways. Despite temperatures far below freezing by Earth standards, liquid water exists here because of the unique chemistry. As water droplets crash into ice crystals, the clouds become electrically charged, sparking lightning. But Jupiter's lightning isn't just bigger, it's on a whole different scale. Juno's microwave radiometer, designed to measure water and ammonia deep in the atmosphere, revealed lightning strikes that may be 100 times more powerful than those on Earth. Some scientists have even suggested flashes 1,000,000 times stronger might occur. During certain close flybys, Juno recorded an average of 3 lightning strikes every second, tallying over 200 electrical pulses in a single pass. So how does Jupiter build such monstrous storms? It comes down to the atmosphere's composition. Unlike Earth, where water vapor is lighter than air and rises easily, Jupiter's atmosphere is mostly hydrogen and helium, and water vapor actually weighs more than the surrounding gas. That means storms need a huge surge of energy to push water vapor upward. When they finally do rise, all that pent-up energy releases in violent updrafts that build cloud towers more than 100 kilometers tall, roughly 10 times the height of storms on Earth. These storms also produce something straight out of science fiction: mush balls. Scientists coined this term to explain a long-standing mystery about Jupiter's atmosphere. Ammonia gas was disappearing at depths far greater than any storm mechanism could account for. It was as if something was dragging it down out of sight. What's happening, according to Juno's data, is this: during the most intense storms, updrafts launch tiny ice particles more than 60 kilometers above the visible clouds. At those heights, ammonia vapor acts like a natural antifreeze, melting the ice into a slushy liquid. As these particles cycle up and down, they grow bigger, collecting more water and ammonia until they form dense, ice-coated slush balls. Heavy enough, these mush balls fall deep into Jupiter's atmosphere, carrying water and ammonia far below the storm's origin. New research published in 2025 confirmed this process, detecting radio signals during storms that couldn't be explained any other way. Deeper and deeper inside Jupiter, pressure rises to staggering levels. At around 1,000 kilometers beneath the clouds, hydrogen gas undergoes a radical change. It doesn't cool into a liquid like on Earth. Instead, the crushing pressure forces hydrogen molecules so tightly together that they become a liquid, despite temperatures soaring above 1,000 degrees. This is the largest ocean in the solar system, an ocean of liquid hydrogen stretching roughly 20,000 kilometers deep, about 2,000 times deeper than Earth's oceans. But the surprises keep coming. Even deeper, under pressures millions of times greater than Earth's surface and temperatures near 10,000 degrees, hydrogen transforms yet again. The electrons normally bound to hydrogen atoms break free, flowing freely through the liquid. This metallic hydrogen behaves like a conductor of electricity, a liquid metal. Juno's measurements suggest this metallic hydrogen layer is the source of Jupiter's intense magnetic field, which is more than 15 times stronger than Earth's in some regions, and in places over 50 times as powerful. Juno also uncovered something never before seen on a planet. Jupiter's magnetic field changes over time, a phenomenon called secular variation. While scientists had observed this on Earth, Juno was the first to confirm it elsewhere. These changes seem driven by deep atmospheric winds that shear and stretch magnetic field lines. One particularly interesting feature is the Great Blue Spot near Jupiter's equator, a localized area of intense magnetic activity invisible to the naked eye but detectable by magnetometers. This magnetic patch drifts slowly eastward, pushed along by the planet's winds, and at its current pace, would circle Jupiter every 350 years. Finally, the biggest mystery awaited at the core. Before Juno, scientists thought Jupiter's center was a dense, compact ball of rock and metal, basically a scaled-up version of Earth's core, maybe 10 times Earth's mass, with a sharp boundary separating it from the layers above. But Juno's gravity data shattered that picture. By analyzing tiny variations in Jupiter's gravitational field and how they affected radio signals back to Earth, Juno revealed a core unlike anything anticipated. Instead of a solid ball, Jupiter's core is enormous and diffuse, blending gradually into the surrounding metallic hydrogen. There's no clear edge where the core stops and the rest of the planet begins. Scientists call it a fuzzy or dilute core. Heavy elements like rock, ice, and metal are mixed throughout this vast central region, spread out over about a third of Jupiter's radius. In total, the heavy materials inside may weigh more than 100 Earth masses, but they're dissolved in hydrogen and helium, creating a gradual transition rather than distinct layers. This discovery has profound implications for how giant planets form. The prevailing theory, called core accretion, says a solid core forms first, gathering rock and metal, then gravity pulls in gas to build the massive envelope around it. This model predicts a clear, compact core at the center. But Juno's findings suggest something far more complex. Scientists have proposed several explanations for this diffuse core. One idea is that as Jupiter formed, incoming solid material dissolved and mixed with gas during formation, creating gradual composition gradients. But simulations show that once the planet started rapidly pulling in hydrogen and helium, any gradients would have been diluted, making this explanation insufficient for Jupiter's large fuzzy core. Another theory suggested a giant collision early in Jupiter's history. A massive, rocky body, perhaps 10 times Earth's mass, could have smashed into Jupiter, stirring up the core and spreading heavy elements throughout the interior. This was a popular idea for years, but recent high-resolution simulations run in August 2025 by teams at Durham University, NASA, SETI, and the University of Oslo used cutting-edge supercomputers to test various impact scenarios. None produced a stable diffuse core. Instead, after the initial chaos, heavy materials settled back into a compact core with a sharp boundary, opposite of what Juno observed. This leaves a third, increasingly favored idea. Jupiter's dilute core formed gradually over millions of years as the planet slowly accumulated both heavy and light materials. Updated formation models show that composition gradients naturally arise when giant planets build themselves up, with heavy elements spread throughout the interior in decreasing concentrations from center to edge, no sharp boundaries needed. Juno's mission has rewritten the textbook on Jupiter, revealing a world far more dynamic and mysterious than ever imagined. The giant planet's secrets, its roaring winds, powerful storms, shifting magnetic fields, and fuzzy core, are reshaping our understanding of how planets grow, both in our solar system and across the cosmos. Jupiter's storms, shifting magnetic fields, and puzzling core are rewriting everything we thought we knew about how giant planets form and evolve, not just in our own solar system, but across the galaxy. Early in Jupiter's life, gradients formed within its interior, and these layers may have stayed intact thanks to a kind of stable layering, where different compositions prevent major mixing for billions of years. This idea of a gradual buildup inside Jupiter is gaining traction, especially because Saturn seems to share the same unusual interior makeup. Although Juno never visited Saturn, the Cassini spacecraft spent over a decade orbiting the ring giant before it was intentionally sent plunging into Saturn's atmosphere in 2017. Cassini's gravity data, combined with seismic clues obtained from Saturn's rings, painted a picture of Saturn's insides as a large, diffuse region with a mixed composition, no sharp boundaries, heavy elements dissolved throughout, much like what Juno found at Jupiter. Considering that Jupiter and Saturn differ so much in mass, temperature, and history, it's tough to argue that each ended up with a fuzzy core because of some rare, one-off event like a massive collision. Instead, it looks like these dilute cores are a normal feature of giant planets. If this turns out to be true, the implications stretch far beyond our own neighborhood. Astronomers have discovered thousands of exoplanets orbiting other stars, many close in size to Jupiter and Saturn. For years, models assumed these distant giants had the same neat structure we once believed for our own gas giants, a compact core of heavy elements wrapped in clean layers of hydrogen and helium. But if Jupiter's interior is actually a messy blend of gradients extending deep down, with no clear core, then those assumptions need a serious overhaul. What we observe in a planet's atmosphere might not reflect its true internal makeup. The chemistry above the clouds could be misleading. For example, phenomena like the mush balls, hailstones made of ammonia and water ice, might be mixing and hiding material beneath the visible layers, making the atmosphere seem more uniform than it really is. What looks simple on the surface can be wildly complex underneath. Before Juno, every spacecraft that visited Jupiter took paths roughly along the planet's equator, meaning the poles remained a mystery. Juno changed the game. Flying over the north and south poles on every orbit, it revealed something no one had predicted. At the North Pole, Juno found a massive central cyclone surrounded by 8 others, arranged like a ring bowing toward the center storm. Each cyclone stretches over 2,500 miles across, and their swirling arms press against one another, yet none of them merge. They hold their ground in a surprisingly stable geometric pattern. Down at the South Pole, a similar setup appears, with 6 cyclones encircling a 7th in the middle. On later passes, Juno even spotted a new cyclone joining the southern cluster, indicating these storm patterns can evolve yet remain stable. Scientists are still scratching their heads, trying to figure out what keeps these storms from blending together, and what physics govern their unusual formations. Juno didn't just answer questions, it created a whole new set of mysteries. By mid-2021, Juno had completed its primary mission, but the spacecraft remained healthy and full of new discoveries to make. NASA extended its mission twice, with final plans to end in September 2025, when Jupiter's gravity will pull Juno into its atmosphere. During this extended mission, Juno's orbit brought it close to 3 of Jupiter's 4 massive Galilean moons, the same ones Galileo first spotted over 4 centuries ago. In June 2021, Juno flew within 652 miles of Ganymede, the largest moon not only of Jupiter but in the entire solar system. This was the closest any spacecraft had come to Ganymede since the Galileo probe's flyby in the early 2000s. That encounter changed Juno's orbit, shortening its orbit from 53 days down to 43, setting the stage for more moon encounters. Then, in September 2022, Juno zipped past Europa, a moon cloaked in an icy shell covering a vast, salty liquid water ocean. For decades, scientists have gathered evidence pointing to liquid water beneath Europa's frozen exterior, one of the most exciting prospects for potential habitability beyond Earth. Juno's microwave radiometer gave the best measurements yet of Europa's ice thickness and structure, helping scientists understand what lies beneath the surface. In December 2023 and February 2024, Juno made its closest approaches to Io, the innermost Galilean moon and the most volcanically active world in the solar system. The images Juno sent back showed fresh lava flows in places mapped by previous missions, confirming Io's intense geological activity is ongoing and unlike anything else we've seen. These moon flybys weren't part of Juno's original mission plan. They were bonus science, made possible by the extended mission and Juno's evolving orbit, discoveries that were never anticipated when the spacecraft first launched. Scott Bolton, Juno's principal investigator, once called Jupiter the Rosetta Stone of the solar system. The idea is that cracking Jupiter's secrets could unlock the story of how the rest of the solar system formed. After nearly a decade of data, that key is still being shaped. The fuzzy, diffuse core inside Jupiter is a confirmed reality, and it forces scientists to rethink how the planet formed. The leading theory points to gradual accumulation of material over time, but it's far from certain. The exact makeup of Jupiter's interior remains only partially mapped. Temperatures deep inside, which influence how scientists interpret composition gradients, are still uncertain. Even estimates of how many heavy elements are dissolved throughout the planet vary depending on which models are used to analyze the gravity data, and those models don't all agree. Juno also confirmed that Jupiter's powerful atmospheric winds reach nearly 2,000 miles beneath the cloud tops. Yet the forces driving those winds, how they interact with the planet's magnetic field and interior, remain under investigation. The polar cyclone's stable geometric arrangements still defy full explanation. The Great Blue Spot, a newly discovered storm, drifts slowly eastward, shaped by surface winds shearing magnetic field lines, a phenomenon no one could detect before Juno's magnetometer. As for the mush balls, the data strongly supports their existence, but the extent to which they influence Jupiter's atmosphere and what that means for the planet's internal composition is still being worked out. Beneath Europa's ice, in an ocean that might have persisted for billions of years, Juno began probing questions that future missions will continue to explore. The Europa Clipper spacecraft, launched in October 2024, is set to reach Jupiter in April 2030. The European Space Agency's JUICE mission, launched in April 2023, will arrive in 2031. Both will study these moons in far greater detail, building on what Juno revealed. Jupiter is a strange giant. It dominates the solar system, weighing more than all the other planets combined, big enough to fit 1,000 Earths inside, yet it remains elusive. Its interior is inaccessible. No probes can drill down or sample its core directly. Scientists must infer everything from afar, using gravity measurements, radio signals, and subtle distortions in space caused by its mass. Juno's greatest lesson is that 4 centuries of assumptions about Jupiter's interior were incomplete, not wrong out of neglect, but simply because the data to show the full picture didn't exist. When Galileo first spotted Jupiter's 4 largest moons as points of light in 1610, that was the limit of human knowledge. Over time, missions like Pioneer, Voyager, Galileo, and now Juno have peeled back layers of mystery. Juno flew lower than any spacecraft before, peering through storms and revealing an interior that isn't neatly layered but spread out, blended, and baffling. The core isn't a single compact mass at the center, it's diffuse, spread throughout the planet in a way that challenges old ideas. The core is everywhere and nowhere at once, fading seamlessly into surrounding layers. Juno made these measurements, transmitted the data back, and forced a rethink of what Jupiter really is. Science thrives on these surprises. The older the question, the stranger the answer often turns out to be. Jupiter has been shining in the night sky long before humans existed. It's only now that we're starting to decode what's really going on beneath those swirling clouds. One of Jupiter's most famous features is a storm that has raged nonstop since at least the 1600s, the Great Red Spot. It's the most iconic storm in the solar system, a crimson hurricane that's fascinated astronomers for centuries. For a long time, all anyone really knew was that it was enormous, it was red, and it spun relentlessly. Juno revealed how deep this storm actually reaches, about 200 miles straight down into the ammonia clouds below. To put that into perspective, Earth's deepest ocean trench is roughly 7 miles deep. The Great Red Spot plunges nearly 50 to 100 times deeper than Earth's oceans. It's not just a surface phenomenon, it's a towering column of rotating atmosphere anchored deep within Jupiter's layers by forces still not fully understood. But the storm is shrinking. When Voyager flew by in 1979, the Great Red Spot was about twice Earth's diameter. By Juno's arrival, it had shrunk to around 1 1/3 times Earth's width. That's still massive, but the trend is clear and measured. Something about the storm's energy, the surrounding jet streams, or the atmospheric dynamics is changing slowly. Whether the storm will keep shrinking, stabilize at a smaller size, or eventually fade away is still unknown. The physics behind its longevity and potential demise remain open questions. The storm's red color is another mystery. The cloud tops of the Great Red Spot rise higher than any other clouds on Jupiter, exposing them to more ultraviolet sunlight. This extra UV light triggers chemical reactions in the storm's compounds, producing the deep reddish-brown pigment that colors the storm. In a way, the storm's color is painted by sunlight. The higher it reaches, the redder it glows. Imagine that, a storm 200 miles deep, colored by the sun, spinning nonstop since before the American Revolution, outlasting every government and empire since people first noticed it in the sky. Juno's close flybys gave humanity the first glimpse of just how deep this storm goes. Yet, why it endures so long remains a profound mystery. Juno's journey to Jupiter wasn't easy. Jupiter's magnetic field is the strongest of any planet in the solar system, about 15 times stronger than Earth's overall, and in some spots over 50 times as intense. This magnetic field sweeps through space like a colossal invisible arm, accelerating charged particles, electrons, protons, and heavier ions, to extreme energies. The environment around Jupiter is so radioactive that ordinary spacecraft electronics would fry in minutes. Engineers built Juno to survive this gauntlet. At its core is a first-of-its-kind titanium vault, about the size of a car trunk and weighing around 400 pounds, shielding the most sensitive instruments and computers from radiation. This vault absorbs the punishment of Jupiter's radiation belts while keeping the science gear safe and functional. Even with this protection, the mission's path was carefully planned. Juno approaches Jupiter from the north, dives between the planet and the inner radiation belts, then swings out over the South Pole before heading back out into space. Each close pass brings Juno within roughly 2,200 miles of the clouds. To visualize that, if Jupiter were the size of a basketball, Juno would skim less than a quarter-inch above its surface. Before Juno, scientists knew Jupiter had a powerful magnetic field, thanks to Pioneer and Voyager missions decades earlier, but Juno showed it's even more intense and far less uniform than expected. The field has lumps, irregular patches, and concentrations popping up where no one predicted. These variations are crucial clues about how Jupiter's magnetic field is generated. On Earth, the magnetic field comes from the movement of molten iron in the planet's outer core, a deep, compact dynamo. Juno's data suggests Jupiter's magnetic field is generated much closer to the surface, within the layer of liquid metallic hydrogen, instead of deep at the center. This shallow dynamo challenges previous ideas and opens new questions about the planet's inner workings. Jupiter continues to surprise, and thanks to Juno, the giant planet's secrets are slowly coming into view, a complex, layered, and endlessly fascinating world, far different from the neat, simple picture imagined for centuries. Jupiter's magnetic field isn't just powerful, it's wildly complex. Because of the enormous layer of metallic hydrogen inside the planet, the magnetic field takes on a tangled, multi-lobed shape, far beyond the simple bar magnet-style dipoles seen on Earth. At the giant planet's poles, this magnetic chaos fuels auroras unlike anything we experience here. Charged particles slam into the atmosphere with energies reaching 400,000 electron volts, hundreds of times more intense than Earth's most powerful northern lights, which max out at just a few thousand electron volts. These aren't gentle, shimmering curtains of light. They're fierce, non-stop electrical storms driven by processes fundamentally different from those lighting up Earth's skies. Jupiter's magnetosphere, the massive bubble carved out in space by its magnetic influence, is staggering in scale. On the night side opposite the Sun, it stretches all the way out to Saturn's orbit. If it were visible from Earth, it would dwarf the full moon, appearing several times larger in the sky. It's one of the largest known structures in the solar system. Yet, before NASA's Juno spacecraft arrived, scientists barely scratched the surface of understanding this colossal force field. Back in December of 1995, NASA's Galileo spacecraft dropped a probe into Jupiter's thick cloud layers. The probe sent back data for about an hour before succumbing to the crushing pressure and heat deep in the atmosphere. What it revealed was confusing. The air it sampled was surprisingly dry. Water levels were only about 1/10 of what scientists expected based on existing models of Jupiter's composition. That was a big deal because water is supposed to be one of the most plentiful molecules in a gas giant's atmosphere. Either the models were off, or the probe had landed in a strange, unrepresentative spot. For over 20 years, that question lingered. Then came Juno, which finally cracked the mystery wide open. Galileo's probe hadn't made a mistake. The landing site was carefully planned. But it just happened to descend into a dry patch, an anomaly in an atmosphere that's anything but uniform. Thanks to Juno's detailed mapping, scientists now know that water is much more abundant near the equator and deeper in Jupiter's atmosphere. The Galileo probe had just sampled a rare dry pocket in an otherwise water-rich world. This discovery is more than a curiosity. The amount of water in Jupiter's atmosphere is a key clue to how the solar system formed. Water, or more precisely oxygen locked in water molecules, acts like a chemical fingerprint tracing the makeup of the primordial disk of gas and dust that birthed the planets. If Jupiter gathered its material as the models suggest, the water content should reflect the environment in the early solar system where Jupiter grew. The unexpectedly dry readings from Galileo created a real conflict with those formation models. Juno's findings showed that conflict was a false alarm, just a result of sampling the wrong place. But there's a bigger takeaway here. If Jupiter's water is this patchy, and a single probe can give a wildly misleading picture, then trying to understand a planet's overall makeup from just one atmospheric sample is much trickier than anyone thought. And if it's this hard for Jupiter, a planet we can study up close with dedicated spacecraft, imagine the challenge of reading the atmospheres of thousands of exoplanets hundreds or thousands of light years away, using only faint light filtered through their clouds. The simple truth emerging from researchers analyzing Juno's data is this: the very top of a planet's atmosphere may not be a good reflection of what lies beneath. That insight could change how scientists approach the study of gas giants forever. Juno's arrival wasn't the first visit to Jupiter, but it was the latest link in a long chain of exploration. In the early 1970s, Pioneer 10, Pioneer 11 became the first spacecraft to venture into the outer solar system. They confirmed that Jupiter's intense radiation environment was barely survivable and returned the first close-up images of the planet. Then, in 1979, Voyager 1 and Voyager 2 took the world by storm, revealing just how alien Jupiter truly is. They showed us turbulent cloud bands, detailed views of the Great Red Spot, and the spectacular volcanic eruptions on the moon Io. From 1995 through 2003, the Galileo orbiter circled Jupiter, deploying its atmospheric probe and uncovering tantalizing hints of a subsurface ocean beneath Europa's icy crust. Galileo mapped Jupiter's moons with unprecedented precision, raising new questions even as it answered others. Each mission built upon the last, peeling back layers of mystery but leaving some puzzles unsolved, puzzles that Juno has now taken on. It's probing the nature of Jupiter's fuzzy core, trying to unravel the origin of the persistent polar cyclones, and revealing the deep atmospheric structure. These questions aren't closing chapters, they're opening new ones, to be tackled by future missions. NASA's Europa Clipper, launched in October 2024 and set to enter Jupiter's orbit in April 2030, will dive deeply into Europa's ice shell and hidden ocean with instruments Juno didn't carry. Meanwhile, the European Space Agency's JUICE mission, launched in April 2023 and scheduled to arrive in 2031, will study Ganymede, Callisto, and Europa before orbiting Ganymede itself, the first ever spacecraft to circle a moon beyond Earth's. Both missions owe a debt to Juno. The radiation data Juno collected around the Galilean moons helped engineers design instruments that can survive and operate in those harsh environments. Juno's insights into Europa's icy shell guided scientists on what to look for and how deeply to probe. Science moves forward step by step, each mission passing the torch to the next. Juno itself carried a unique symbol of that heritage, a small aluminum plaque from the Italian Space Agency. Etched onto it was a self-portrait of Galileo Galilei alongside a passage from his journal, handwritten by the man himself. It was the January 1610 entry where Galileo first described the 4 points of light near Jupiter that would later bear his name. The spacecraft designed to uncover what Galileo couldn't see carried his words with it into orbit over 400 years later. There's something almost poetic in that. Galileo wrote that around Jupiter there are moving stars invisible, until that time to everyone. He was right, they had been invisible until then. But what he couldn't have imagined was how long their secrets would remain hidden, how many layers of mystery still awaited discovery. It took a week for Galileo to confirm his moons. 3 more centuries to even begin reading Jupiter's atmosphere. And only now, with Juno's precise gravity measurements and nearly a decade of data, are we starting to glimpse the planet's true interior. Even today, the core isn't a clear, hard boundary, it's fuzzy, blending imperceptibly into the surrounding metallic hydrogen. The science itself is still evolving. What's known about Jupiter now surpasses anything previous generations could dream of, but it's almost certainly less than what future explorers will uncover. That gap between what's learned and what remains unknown isn't a failure. It's the nature of every meaningful question. Jupiter is still out there, spinning in space, holding its deepest secrets behind clouds no instrument has fully penetrated. The Great Red Spot continues its eternal whirl. The polar cyclones maintain their intricate dance. The fuzzy core quietly blends into the liquid metal layers above, like a secret hidden in plain sight, waiting for instruments precise enough to finally read its story. And humanity is building those instruments.